Welcome to this explainer. Today, we're going to look at coordinate geometry in a completely different light. Seriously, forget the idea that this is just some tedious list of abstract formulas you're forced to memorize for a test. Instead, I want you to see this as a tangible, highly logical toolkit. We are literally learning how to draft the architectural blueprints of mathematical structures. With just a handful of variables, we can define infinite space. So let's get building.
Okay, let's dive right into this. Here's our roadmap. We are starting from the absolute ground floor with the Cartesian foundation, then we'll start building a straight line. After that, we'll look at intersections and line dynamics, step it up with advanced systems and transformations, and finally, reward ourselves with some high-yield geometry hacks.
Section 1. The Cartesian foundation. Because, as we all know, every solid, lasting structure needs a perfectly mapped foundation before you can even think about building on it.
To really ground ourselves, we need a rigorous definition. A straight line isn't just a random ruler mark on a piece of paper. Mathematically speaking, it is the locus, or, the continuous path, of all points that satisfy a linear equation in x and y. Think of it as a strict set of rules. A line is simply a collection of points that obediently follow an algebraic law. Basically, if a point doesn't fit the equation, it doesn't get to be on the line. No exceptions. And this brilliantly illustrates how that works in practice. On our foundational grid, a single point P is defined by its horizontal displacement, the abscissa, and its vertical displacement, the ordinate. But look over the panels on the right. When those points link up according to our algebraic law, they form lines that interact with this space in highly specific ways. They slice through the axes to create intercepts, they might skew across the grid as oblique lines, or they can simply align in perfect harmony as collinear points.
Section 2. Building a straight line. Now that our foundation is set and perfectly surveyed, we can safely transition to the construction phase. We're taking that empty grid and starting to build the actual frame of our line.
But before we drop a heavy payload of algebra onto our grid, ask yourself this absolutely fundamental question. How do we actually measure the exact direction or the steepness of a line? I mean, if you're building a ramp or pitching a roof, you need a precise number for that incline, right?
Well, that brings us to slope. Now, what's really interesting about this slide is the behavior scale down at the bottom. The slope, which we represent with the letter m, is our ultimate directional compass. It's simply the change in y over the change in x, the classic rise over run. But look at how elegantly this translates to instant visual understanding. By simply calculating m, you instantly know the line's behavior. If m is greater than 0, it slants up. Less than 0, it slants down. If it's exactly 0, you've got a perfectly flat horizontal floor. And if you try to divide by 0, well, the math breaks down because it's undefined, which gives you a sheer vertical wall.
With slope securely in our toolkit, we arrive at the master blueprint of this entire explainer, the equation decision tree. You see, you never need to arbitrarily guess which equation to use. It purely depends on what specific information you currently hold in your hand. Got a slope and a y-intercept? Grab the slope-intercept form. Just have two random points? Grab the two-point form. Every single form you see here uniquely describes a line. They are literally just different algebraic tools to arrive at the exact same geometric truth.
So the crucial point here is knowing exactly when to deploy which tool. On the left side, we have point dynamics. You're going to use the slope-intercept form or the point-slope form when you're dealing with the internal movement of the line, like when you know its angle in a single anchor point. But over on the right, notice how we switch tactics entirely. When you're dealing with boundary constraints, meaning you know exactly where a line crashes into the x and y axes, the intercept form is far, far more efficient and builds the line directly from its boundaries.
Ultimately, though, all these specific forms can be reorganized into the general standard form, ax plus by plus c equals 0. This is the universal language of straight lines, and what makes this form so incredibly powerful is the elegant algebraic extraction keys shown on the right. If you have the general form, you don't even need to graph it to understand it. You can instantly pull the slope out by just dividing negative a by b. You can instantly find the intercepts. It's just a perfectly packaged summary of the line's entire existence. Section 3. Intersections and line dynamics. Okay, so we've built our lines. But honestly, a blueprint with only one line isn't very interesting. Phase 3 is where lines start crossing paths, colliding, and really interacting in the same spatial grid.
When two lines exist in the same plane, their slopes tell the whole story of their relationship. On the left, we see parallel lines. They are perfectly synchronized. They share the exact same slope, m1 equals m2, meaning they will run alongside each other into infinity without ever touching. On the flip side, perpendicular lines perfectly oppose one another.
Their collision is so absolute that if you multiply their slopes together, the result is always exactly -1. No exceptions.
Let's move on and see how this builds into intersection mechanics. When lines aren't parallel, they collide, and that collision creates an angle. We can use the tangent formula right here to calculate the precise angle theta between any two colliding lines, just by plugging in their slopes. If the numerator evaluates to 0, boom, the lines are parallel. If the denominator evaluates to 0, you've got a perfect 90-degree perpendicular intersection. It's like a built-in cross-check. So, intersections are all about collision, but what about separation? Let's map out the spatial reality of distance geometry. On the top, we have the formula for the absolute perpendicular distance from a lone floating point down to a straight line. Notice those absolute value bars. That's because distance in the physical world is always positive. You can't have negative distance. On the bottom, we see how to measure the constant gap d between two parallel tracks. By just comparing their constant values c1 and c2, we can measure the void between them without ever needing to pull out a ruler.
Section 4. Advanced Systems and Transformations. Now, if you're a focused learner aiming for those high-level engineering scenarios, this is exactly where we upgrade our toolkit. We are moving way beyond single lines and diving headfirst into dynamic, advanced systems.
Think about this. Instead of plotting one line at a time, what if we want to plot an infinite number of them? By taking two intersecting lines, L1 and L2, and combining them with a lambda parameter, we create a family of lines. As you change that lambda value, the new line spins around that original intersection point like a propeller. Pretty cool, right? And if you have three separate lines and want to know if they perfectly collide at a single point, a state we call concurrency, you simply drop their coefficients into a 3x3 determinant. If that determinant equals 0, you've got a perfect three-way collision.
We can also use lines as tools to manipulate other points. Notice the elegant algebraic symmetry of finding a reflection here. You're treating the line as a perfect mirror, and you can find the exact coordinates of the reflection on the other side. Actually, look really closely at that bottom formula. You absolutely must watch out for that crucial multiplier of -2. That -2 is the secret sauce. It's what pushes the point past the foot of the perpendicular and fully across the mirror's surface.
And now for the ultimate architectural power move. Sometimes a mathematical problem is just incredibly complex because the line is drawn awkwardly across the grid. Well, instead of redrawing the complex line, you can use these transformation formulas to literally translate or rotate the entire universe, the axes themselves, around the line. You can shift the origin to a new point or rotate the x and y grid by an angle theta. The line stays perfectly still and the world moves around it, simplifying the math instantly. It is a total game changer.
Section 5. High-yield geometry hacks. You've mastered the foundations, the building phase, the intersections, and the transformations. So, as a reward for making it this far, this final section is dedicated entirely to high-yield, time-saving shortcuts that are absolute lifesavers for exams.
When time is of the essence, you really don't want to derive everything from scratch. You need rapid coordinate hacks. We can instantly find the area of a coordinate triangle using just its vertices, no base or height needed. We can pinpoint the exact center of gravity, the centroid, by simply averaging the x and y coordinates. And my favorite, we can drop parallel lines onto a graph almost instantly using algebraic offsets. Let's anchor those concepts visually. Look at the top two panels. You can see how incredibly efficiently the area and centroid formulas utilize the raw vertex coordinates. But I really want to draw your attention to the bottom panel, the parallel offset trick. If you're given a line and you need to build a parallel wall right next to it, please don't waste time recalculating slopes. Just keep the a and b coefficients, the x and y parts, perfectly identical and simply introduce a new constant d. Boom! Instant parallel line, zero stress.
We started today with an empty grid and a very basic definition. And now? Now you hold the tools to construct families of lines, reflect points across dimensional mirrors, and literally rotate the mathematical universe to your advantage. Coordinate geometry isn't just some boring subject. It's honestly a superpower. With just a few variables, you can build, reflect, and shift the geometry of an entire universe. So, looking at the complex world around you, what will you calculate next?